And I just did a calculation this morning. You are the first one to hear that the object will come closest to Jupiter on March 16th, 2026, and it will arrive exactly.
3I Atlas is now approaching Jupiter's hill sphere, the invisible frontier where the planet's gravity finally evens out against the pull of the sun. And this is the moment that has astronomers completely stunned. The object is arriving with a precision deviation of just 1 part in 26,000. To put that into something human, it's like standing in Los Angeles, throwing a sewing needle across the entire continent and having it land perfectly on the rim of a coin resting in New York. After crossing billions of miles of interstellar space, enduring chaotic solar heating, and navigating layers of gravitational turbulence, 3I Atlas is sliding into a region 33.24 million miles from Jupiter with a margin of error of barely 35,000 meters. No naturally behaving comet has ever demonstrated this kind of controlled arrival. Over 230 observatories across the globe documented the course shift. It happened immediately after perihelion, the exact moment when a trajectory correction would have the maximum effect and the minimum energy cost to redirect an object toward this boundary. If you've been tracking 3I Atlas from the beginning and this sudden precision feels almost impossibly calculated, hit subscribe, tap like, and let's break down the numbers, the maneuver, and the 3 scenarios scientists are preparing for as 3I Atlas reaches Jupiter's edge. Because what happens after this could reshape our understanding of interstellar visitors. When 3I Atlas first entered detectable range from deep interstellar space, it followed a completely normal hyperbolic path. Its speed, inclination, orbital shape, everything aligned perfectly with expectations for an object not born in our solar system. Astronomers logged it as another rare passerby. Unusual, but not unprecedented. Then it began approaching the sun, and that's when things shifted. After perihelion, the closest pass around the sun, the object began displaying non-gravitational acceleration. On its own, this isn't unusual. Comets often experience this when solar heating vaporizes surface ice and releases jets of gas that push them like tiny thrusters. But those jets are normally chaotic. Comets tumble, rotate unpredictably, and their outgassing happens in bursts. One jet fires stronger, another weaker, directions cancel each other out, and the motion becomes messy. Their paths become hard to predict. But 3I Atlas broke the pattern. Its acceleration was small, but extremely directional. It nudged the object just off its expected track, but the angle of that nudge aligned almost perfectly with the vector needed to arc it toward Jupiter's hill sphere. Not close, not approximate, almost flawless. More than 200 observatories independently measured the deviation and arrived at the same finding. The object was no longer following a purely gravitational orbit. Every updated model brought the new path closer and closer to an ideal match with the boundary of Jupiter's hill sphere. This level of agreement across so many international datasets makes the course shift remarkably hard to dismiss. The acceleration was precisely the strength required to produce the correction we're seeing now. If it had been even slightly stronger or weaker, 3I Atlas would miss the region by millions of miles. The timing is just as critical. The adjustment began abruptly after its solar pass, the exact place where even a minor push could cause the largest long-term course change. A correction earlier or later wouldn't send it to this narrow zone at all. The phenomenon could still be natural, but the combination of timing, accuracy, and directional consistency has kept astronomers questioning whether normal outgassing alone can explain it. To grasp how extraordinary this precision is, you need to understand how interstellar objects typically behave. They enter the solar system spinning unpredictably with irregular surfaces that heat unevenly under sunlight. The smallest variations in temperature, rotation, or shape push them in random directions, producing paths that drift and wobble. Models must include enormous error bars, often millions of miles wide. Predictions tend to get less certain over time. 3I Atlas isn't following that trend. Instead of its trajectory uncertainty growing, every new observation tightens it. The error margins shrink instead of expanding. The object is following a path so clean and stable that it no longer resembles the messy acceleration patterns comets normally display. This isn't gentle drift over months. The correction began sharply, right after its solar pass, sending it directly toward the narrow region surrounding Jupiter's hill sphere.
The probability of a natural jet firing at exactly the right strength and direction at exactly the right moment is extremely low. This is why researchers are struggling to explain the effect through standard comet physics. The behavior resembles a final course adjustment maneuver, something spacecraft use to refine their approach rather than a random puff of gas. Here's the analogy. Imagine throwing a dart blindfolded from one continent and hitting a bullseye on another. Now imagine that halfway through the flight, the dart nudges itself to compensate for wind, atmospheric drag, and gravity, all without any guidance system. That's the type of precision we're witnessing with 3I Atlas. Natural forces rarely produce this level of accuracy across interstellar distances. To understand why this matters, we need to understand the Hill sphere. It marks the region where a planet's gravity becomes stronger than the sun's pull. For Jupiter, this shell stretches tens of millions of miles across. Natural objects almost never strike its boundary precisely because their motions are governed by chaotic forces, radiation pressure, dust impacts, uneven venting. They either fall inside Jupiter's gravity well or remain comfortably outside it. The boundary functions more like a mathematical threshold than a real physical target. Very few natural bodies ever cross the edge cleanly, let alone aim for it. And yet 3I Atlas is arriving at this thin gravitational balance with unnerving accuracy. The transition is especially important because crossing it changes everything. Outside the Hill sphere, the sun dominates motion. Inside it, Jupiter takes over. The slightest shift in velocity or angle at that border can send an object into capture, acceleration, slingshot, or ejection. The futures diverge drastically based on tiny differences. Space agencies depend on this principle. Engineers routinely use Jupiter's gravity to perform slingshot maneuvers, adjusting trajectories using gravity's leverage instead of fuel. Reaching these gravitational boundaries normally demands precise calculations and flawless timing because even the smallest misalignment can push a spacecraft into a completely different future orbit. Missing the Hill sphere edge by only a few thousand miles can alter a mission's path by millions of miles later. Even with modern guidance systems, it's a difficult target for human technology, which is why watching an interstellar object behave with similar accuracy is raising serious questions about what forces are influencing it.